Randomness is one of the most misunderstood words in all of science, largely because the human mind instinctively associates it with failure, breakdown, or absence of control. When we see unpredictable outcomes, scattered motion, or irregular patterns, we label them chaotic and assume they are meaningless. But in physics, randomness does not mean that reality has stopped following rules. It means that the rules allow multiple outcomes, and which one occurs cannot be predicted in detail without complete information. Randomness is not the opposite of order. It is the condition under which order can emerge without being pre-written. A perfectly ordered universe would be static, frozen into a single configuration with no room for novelty. A completely random universe would dissolve into noise. The universe we inhabit exists in between, where randomness supplies variation and physical laws constrain it, allowing patterns to form gradually instead of being imposed from the start. In everyday life, we confuse randomness with disorder because we experience only small slices of reality and expect immediate explanations. When a system's behavior exceeds our predictive ability, we assume it lacks structure. But many systems governed by strict rules still produce outcomes that appear random at human scales. Weather patterns follow physical laws, yet precise prediction quickly becomes impossible. The motion of gas molecules obeys mechanics, yet individual trajectories feel unknowable. This is not because the universe is sloppy, but because complexity amplifies uncertainty. Randomness, in this sense, is not the absence of law, but the presence of too many interacting variables for simple foresight. The universe does not roll dice in ignorance. It explores possibilities within constraints that are deeper than our intuition. Probability, which we often treat as a confession of ignorance, is actually a language the universe speaks fluently. At fundamental scales, especially in quantum physics, probability is not a temporary placeholder for missing knowledge, but an intrinsic feature of how reality unfolds. Outcomes are not fixed until interactions occur, and even then they are selected from distributions rather than dictated with certainty. This unsettles us because human cognition prefers definite narratives, causes leading cleanly to effects, but the universe is not obligated to satisfy narrative comfort. Probability allows multiple futures to remain open until they are resolved by interaction, and this openness is precisely what allows the universe to remain unfinished rather than locked into a single predetermined story. What appears as noise is often the raw material from which structure forms. Tiny random fluctuations in otherwise smooth systems can be amplified over time, giving rise to large-scale patterns. In the early universe, matter was distributed almost perfectly evenly, with only minuscule variations in density. Those variations were effectively random, yet they became the seeds of galaxies, clusters, and cosmic filaments. Without those irregularities, gravity would have had nothing to work with, and the universe would remain a featureless fog. Randomness did not destroy order, it made order possible. Chaos, in this context, is not an enemy of structure, but its starting point. Human intuition struggles with this because we evolved in environments where randomness often signaled danger or lack of control. A rustling sound in the bushes could mean a predator. An unpredictable environment threatens survival. As a result, our brains are biased to seek patterns quickly and to mistrust situations where patterns are not immediately visible. We project this bias onto the universe, interpreting randomness as a sign that something is broken or incomplete. But from a cosmic perspective, randomness is not a flaw, it is a feature that prevents stagnation. A universe without randomness would repeat itself endlessly, incapable of generating anything new. In physics, randomness does not negate causality, it reframes it. Causes still exist, but they do not always determine a single outcome. Instead, they shape a landscape of possibilities within which specific results emerge through interaction. This is why randomness and law coexist so comfortably. Laws define what is allowed, randomness determines what actually happens within those allowances. The universe behaves less like a script being acted out and more like a game governed by rules that permit many plays. The outcome is not written in advance, but it is not arbitrary either. The mistake is thinking that meaning requires predictability. We assume that if outcomes cannot be foreseen, they must be meaningless. But meaning in the universe does not arise from certainty. It arises from relationship, persistence, and consequence. A random mutation in biology can alter the trajectory of an entire lineage. A quantum fluctuation can leave an imprint that shapes cosmic structure billions of years later. These events are not meaningless simply because they were not predetermined. Their significance emerges over time as they interact with constraints and feedback. Meaning is retrospective as much as it is predictive. Randomness also protects the universe from brittleness. Highly ordered systems that lack variability tend to fail catastrophically when disturbed. Systems that incorporate randomness can adapt, reorganize, and survive change. This is true in physical systems, biological evolution, and even human societies. Variation allows selection, learning, and resilience. In this way, randomness is not destructive but stabilizing across long timescales. It keeps the universe from collapsing into a single fragile configuration. When we say the universe is unfinished, we are not saying it is incomplete in a flawed sense. We are saying it is open-ended. Randomness ensures that the future is not a simple extension of the past. New configurations can arise that were not explicitly encoded at the beginning. The laws of physics do not specify galaxies, stars, life, or minds. They specify constraints within which such things can gradually appear. Randomness supplies the diversity of starting points. Time allows selection and amplification. Together they produce a cosmos that grows rather than merely exists. The discomfort we feel toward randomness is, at its core, a discomfort with uncertainty. We want the universe to be either fully controlled or fully chaotic, because both extremes are psychologically easier to categorize. An unfinished universe resists categorization. It is lawful but unpredictable, structured but creative, stable yet always changing. Randomness is the sign that the story is still being written, not that the story lacks coherence. Seen this way, randomness is not evidence that the universe lacks meaning. It is evidence that meaning is not imposed from the beginning, but emerges through process. The universe does not hand us finished answers. It generates conditions under which answers can form. What looks like chaos at one scale becomes structure at another, given enough time and interaction. Randomness is simply the universe refusing to close itself off too early. To mistake randomness for chaos is to confuse openness with absence. The universe is not empty of direction, it is rich in possibility. Randomness keeps those possibilities alive. It ensures that reality remains a space of becoming rather than a monument to what has already been decided. In this sense, randomness is not the universe failing to make sense. The early universe was not dramatic in the way our imagination prefers. There were no galaxies, no stars, no chemistry, no light sources scattered across space. Instead, there was near uniformity, a hot, dense state where matter and energy were spread with astonishing smoothness. This smoothness is not poetic exaggeration. It is measured directly in the cosmic microwave background, the afterglow of the early universe, which reveals temperature differences of only 1 part in 100,000. To human intuition, such uniformity feels sterile, even boring, but it is precisely this simplicity that made everything else possible. A universe filled with structure from the beginning would have had nowhere to go. The early cosmos was not rich, it was permissive. It began almost empty of form, carrying only the faintest irregularities that would later become the scaffolding of all complexity. After the Big Bang, the universe expanded rapidly, cooling as it did so. Particles formed, annihilated, and eventually stabilized into protons, neutrons, and electrons. But even then, the universe remained nearly featureless. Matter was spread out so evenly that gravity had little to grab onto. There were no dense clumps pulling material inward, no preferred locations where structure could easily begin. This was not a failure of physics. It was a consequence of initial conditions that favored uniformity. The universe was smooth because it had not yet had time to become anything else. Time, not energy, was the missing ingredient. Without duration, complexity cannot accumulate. The early universe was not designed to impress. It was designed, in a sense, to wait. The tiny fluctuations that did exist were almost trivial in magnitude, yet they carried enormous consequence. These were slight over and under densities in matter, statistical ripples left behind by quantum processes amplified during cosmic inflation. At the time, they meant almost nothing. No observer could have looked at the early universe and predicted galaxies from them with confidence, and yet these faint irregularities were enough. Gravity, though weak, is patient. Over millions and then billions of years, it amplified these differences, pulling matter slowly toward regions that were only infinitesimally denser than their surroundings. Complexity did not erupt, it accumulated. The universe did not leap from simplicity to richness. It drifted there, guided by time and imbalance. What matters is not that the early universe was simple, but that it was allowed to be simple. Complexity was not present because it could not yet exist, not because it was forbidden. High temperatures prevented atoms from forming. Density prevented stable structures. Forces behaved differently under extreme conditions. The laws of physics were already in place, but their consequences had not yet unfolded. This distinction is crucial. The universe did not change its rules to become complex, it changed its state. As conditions cooled and expanded, new behaviors became possible. Simplicity was not replaced, it was layered over, buried beneath emergent structures that required time to appear. The idea that the universe began with almost nothing is unsettling because it clashes with how we imagine origins. We expect beginnings to be crowded, chaotic, overflowing with potential fully formed. Instead, the universe began nearly blank. It carried energy, yes, but very little structure, no chemistry, no differentiation, no hierarchy. This emptiness was not absence but openness. With so few constraints active at once, the universe had room to explore what the laws of physics would allow. Complexity was delayed not because it was unlikely, but because it was patient. The universe did not rush toward richness. It unfolded into it. As expansion continued, matter decoupled from radiation, allowing light to travel freely. This moment did not produce complexity either, it merely made the universe transparent. For hundreds of millions of years afterward, the cosmos entered what we now call the cosmic dark ages. No stars yet burned, no galaxies yet shone. Hydrogen-filled space almost uniformly, drifting slowly under the influence of gravity. This prolonged simplicity is often overlooked, but it matters deeply. The universe spent far more time being simple than complex. Complexity is the latecomer. It is the exception, not the rule, and that makes its existence more meaningful, not less. Complexity came later because it required conditions that only time could supply. Cooling allowed atoms to form. Atoms allowed chemistry. Chemistry allowed molecular clouds. Molecular clouds collapsed into stars. Stars forged heavier elements which seeded planets. Planets allowed stable environments where further complexity could arise. None of this was guaranteed by the initial state. The early universe did not contain galaxies in miniature. It contained only the capacity for them. This capacity was distributed almost evenly, waiting for slight imbalances to break symmetry. The universe did not begin as a blueprint for life. It began as a set of permissions. It is tempting to interpret the early universe's simplicity as evidence of fine-tuning or intention, but this misses the point. Simplicity is not precision. It is neutrality. A universe that starts overly complex risks collapsing into fixed patterns too early. A simple beginning avoids premature commitment. By starting nearly uniform, the universe allowed gravity, chance, and time to collaborate in shaping outcomes. This is not design, it is openness. The universe did not know what it would become because knowing requires structure, and structure had not yet formed. The transition from simplicity to complexity was not smooth or inevitable. Many regions remained sparse, becoming cosmic voids that still dominate the universe's volume today. Even now, most of space is nearly empty, with matter concentrated along filaments and clusters separated by vast expanses of darkness. This distribution is a fossil record of the universe's early simplicity. The fact that complexity exists at all is not because the universe was full from the start, but because it was empty enough to let gravity carve structure slowly. Complexity did not fill the universe, it localized within it. This challenges a common assumption that beginnings contain everything in compressed form. In reality, the early universe contained almost nothing recognizable to us. It was hot, dense, and uniform, but not rich. Richness emerged through asymmetry, delay, and accumulation. The universe did not begin as a crowded workshop, it began as an open field. Time was required to introduce differentiation, and entropy ensured that change had a direction.